section, you understood that each pin has got multiple functionalities, what we call as modes, and the functionality of a pin depends on its mode configured in its pad configuration register. In this SoC, there are up to 8 modes from mode 0 to mode 7. And by default, the mode of an I/O pin is configured in mode 7, that is GPIO mode. That's why in the previous exercise, actually, we didn't care about configuring the pad configuration registers of the pins which we used, because in the earlier exercise, we wanted a GPIO configuration. Anyway, by default, the modes will be in GPIO modes. That's why we didn't care about configuring any pad configuration registers. But if you are using an I/O pin for some other functionality other than GPIO, then you must configure the pad configuration register of that pin. You know that each pin has got its own pad configuration register for this SoC. In this lecture, we'll understand the pin control subsystem of Linux, which is used to take care of this pin configuration stubs. Let's understand about this subsystem which helps us to carry out the pin configuration. There are too many blocks in this picture, so don't get intimidated. So let me explain with some example. Let's first start from the hardware. Let's say your goal is to connect an I2C based WFROM to the SoC. How many pins you require? You may be consuming 3 pins of the SoC. 2 pins to carry out the data communication over I2C, and 1 pin maybe to control the WFROM, maybe to assert or deassert the write protect, something like that. So maybe you will be consuming 3 pins. So out of these 3 pins, 2 pins should be in I2C mode. Otherwise, the I2C communication won't work. That's why you have to set up pin configuration for these 2 pins. And for this pin, you may have to configure it as a GPIO. So if you see this example, you can understand that the pin configurations are pretty much common or essential for any hardware interfacing projects. This is a WFROM, a device, or you can call it as a client device, or you can call it even a platform device. There will be one platform driver for this device. Let's call it as a WFROM driver. This WFROM driver controls this WFROM device. You can call it as a platform driver, or you can call it as a I2C client driver, or whatever it is. Simply, we can call it as a consumer driver. There will be one device tree node explaining this WFROM in the device tree file. And when there is a match between this device tree node and this driver, you know that probe function of this driver gets called. And in the probe function, this WFROM can control or configure this device, isn't it? But the WFROM cannot initiate any data transactions or control transaction with the WFROM. Why? Because the pin configuration has not yet done. First, WFROM driver has to carry out the pin configuration. It has to keep these 2 pins in I2C mode, and it has to keep this pin in GPIO mode. Then only the WFROM driver can initiate any control or data transactions with the WFROM. That means that the WFROM driver has to know what are the addresses of the pad configuration registers of these 3 pins. But the good news is, the consumer driver need not to worry about the pad configuration registers or its memory mapped addresses, anything like that. So what the consumer driver can do is, it can just take the services given by the pin control subsystem of Linux. It's a kind of abstraction. The driver can just use the APIs or the helper functions provided by this pin control core of Linux to carry out the pin configuration of the pins. That means the pin controller core of the Linux provides services to the consumer drivers who want to configure the pins. This core you can find in this location, a driver's pin control core.c. Basically, pin controller core implementation you can find in driver's pin controller core.c. This provides pin control helper functions to any consumer drivers. And pin control core of the Linux maintains pin exclusivity for a device. For example, when one device has claimed some pins, then another device, if it tries to claim the same pins, then that claiming fails. This exclusivity is maintained by the pin control subsystem of Linux. Otherwise, what happens? One device claims some set of pins, it changes the pins modes, and after that another device claims the same set of pins and it changes to some other modes. It leads to problems, right? That's why the pin control subsystem also maintains the pin exclusivity for a device. And it also provides debug interface to user space through sysfs. Through sysfs, by running few commands, you can find out the currently configured modes of the pins of an SoC. This is actually hardware independent code. So this subsystem relies on the services provided by the pin controller driver. The pin controller driver knows how to configure the pad configuration registers of the SoC. So there are two types of pin controller driver in Linux. One is vendor provided pin controller driver, and another one is generic device tree based pin controller driver. This is a generic pin controller driver which is given by Linux. Its location is drivers pin control -single.c. So some SoCs, they provide their own pin controller driver. For example, if you just check for STM32 microcontrollers, they provide their own pin controller driver. So for our SoC, that is for OMAP based SoCs from Texas Instruments, it uses pin control single.c. That's a generic device tree based pin controller driver. That's why the flow is like this. First, the consumer driver uses the pin control core's kernel functions to initiate pin configuration, and then the pin controller core of the Linux forwards that request to the appropriate pin controller driver, and then pin controller driver knows how to configure the pad configuration registers inside the SoC. That's how the pins will be configured, like that. Now to summarize this, pin control subsystem of Linux is used to configure pins of a microprocessor or microcontroller. What is pin configuration actually? A pin configuration could be pin mode configuration for alternate functions. It could be slew rate management. It could be driver strength management. A pin configuration also means that managing pull up or pull down resistors. You can enable it or disable it. Pin configuration also means that controlling the output type. Output type could be push pull, open drain, like that. I said for our SoC, the pin controller driver is this one, pin control -single.c. This is actually a driver which is based on device tree nodes for pin configurations. That means this driver works on the device tree what you create for pin configuration. Now let's understand this. Let's say this is your connection details. So now here we can identify various elements here. First thing is, this is a client device or a consumer device, and these are the pins which is going to be consumed, and these pins are handled by the pad configuration registers of the SoC. We call the pad configuration registers as pin controller hardware. For this SoC, the pad configuration registers are nothing but pin controller hardware. That's why you can identify three things here. One is pin controller, and another one is a client device, and another thing is several pins that need to be configured. So that's why to work with this generic pin controller driver, you had to create several device tree nodes. Why? Because that pin controller driver is device tree based pin controller driver. First, you have to create a node which explains the pin controller. And then you have to create a node which explains configuration details for individual pins. First, you have to create one node for explaining the pin controller, create another node which explains the configuration details of individual pins, and then node which claims the pins. That means a device tree node for this client device, which is going to claim the pins. So I hope it is little difficult to understand, but we'll see some examples later. Maybe at that time it will make more sense. To summarize this, very simple concept here. For this SoC, the pad configuration or the pin configuration is taken care by the Linux generic pin controller driver that is actually based on device trees. So it demands you to create several device tree nodes. First, you have to create a device tree node for the pin controller. In our case, the pin controllers are nothing but hardware registers, like hardware pad configuration registers. You have to create one node explaining your SoC's pin controller, but you need not to worry about creating this node because it is given by the higher level DTS inclusion files. And after that, you have to create one node which explains the configuration details of individual pins. This you have to do. Why? Because only you know how many pins you want and what are its configuration. That's why you have to create one node. After that, you have to create one more node which claims the pins. In this case, WPROM node, which claims the pins. What's a pin controller? Hardware modules that control pin multiplexing and configuration parameters such as pull-up, pull-down, tri-state, drive strength are designated as pin controllers. Each pin controller must be represented as a node in the device tree, just like any other hardware module node. For AM335X, the pad configuration registers are called as pin controllers. So now the next question is how to write a pin controller node. This is explained by your pin controller drivers binding document. If you are using generic pin controller driver, then you have to refer pin controller -single.txt, which is there in documentation, device tree, bindings, pin control. Basically, you don't write any pin controller node because, as I said, it is given by the higher level device tree inclusion file. But if you want to explore that, you have to visit that file, pin controller single.txt. You see here, there are a couple of examples how to write a controller node. Basically, you must mention the starting address of the pad configuration registers in your SoC and the offset. And look at the compatible string. The compatible string is initialized to pin control -single. When this pin controller node is detected, the pin controller driver's probe method will get called, and the pin controller driver then passes this address details, and that's how the driver knows the addresses of the pad configuration registers of the SoC. For our SoC, this is a pin controller node which you can find in AM336-L4.dtsi. And its compatible string is initialized to pin controller -single, which indicates this SoC uses generic pin controller driver, which is based on device tree. How to write pin configuration node? The pin configuration node should be written by you, because inside the pin configuration node, you are going to explain the pins which needs to be configured. And this pin configuration node will be the child of this pin controller node. When the probe function of the pin controller driver triggers because of this compatible property, so the pin controller driver goes through all the child nodes of this pin controller and it configures the pins which you mentioned in the pin configuration node. Now the question is how to write a pin configuration node. I mean, what are the properties you have to use to write a pin configuration node? If you want to understand what exactly is the property you have to use to explain the pins, then you should check that in the documentation of the pin controller driver. That is device tree binding documentation. Let's continue with this example. For our WFROM example, this is a parent, that is a device node explaining the pin controller of the hardware. And this is a child node which explains the pins. So you have to use a property called pins. This is a property. You have to use a property called pins to explain the pin configuration of your project. For example, in this case, the exact property name is this one actually. The driver name followed by the name of the property, that is pins. Pin control hyphen single comma pins. So if you are using generic pin controller driver, then you have to use this property. How to use this property? So you have to initialize this property to some value. Let's explore this property. For that, you have to visit the pin controller single.txt. So you have to visit pin control hyphen single.txt. Just search for pin control single comma pins. Here it is. They have explained how to use this property. The pin configuration nodes for pin control single are specified as pin control register offset and value pairs using pin control single comma pins property. So you have to use like this. This is the offset of the pad configuration register, and this is a value which is going to be programmed inside that pad configuration register. Instead of hard coding the values like this, so the SOC gives you some macros which you can directly use. These macros we're going to explore later. Basically, these macros will get turned into these value pairs. But the takeaway from this lecture is not to understand these macros. These are just macros which are explaining the configuration for the pins. So the takeaway from this lecture should be, there is a controller node and your project's pin configuration node is a child of that pin controller node. And inside the pin configuration node, you have to use a property called pins. The exact name is pin control hyphen single comma pins. So that's a property. You have to use that property to initialize the pins which your client device is going to consume. And its format is like this. There should be a angle brackets, and inside that angle brackets, you should mention a value pair, a register offset and value pair. These macros provided by the SOC header files so makes our life easier to manage the register offset and the value pair. We'll explore that later. So now take a look into this slide. This slide actually shows all the three device nodes for this example. First of all, this is a pin controller node. Pin controller node explains the pin controller hardware of the SOC. As I said, it is already given by the higher level device tree file inclusions. And you should create one device tree node to explain the pins, which is this one. So which is a child of this pin controller. And inside that node, you use pins property to explain your pins. We'll see how to use this in later lectures. When the probe function of the pin controller driver triggers, it reads this child node and it gets this information and it configures the pins. Then probe function of the consumer driver will get called. So by the time the probe function of the consumer driver gets called, pins are already configured by reading the information from the device tree. That's why this is called device tree based pin controller driver. And after that, someone has to claim this pin configuration node. That is done by the client device node. This device node actually explains the client. In this case, it is WFROM. Actually, this explains the onboard WFROM of the BeagleBone Black hardware. Actually, I have taken this device tree node from the BeagleBone's device tree file. You see, it has got a compatible string. The driver of this WFROM is Atmel's driver. And you see here, this client device node claims this pin configuration node through these properties. So you see here, in this property, it is claiming this pin configuration node. So these properties you will use in your client device node to claim the pin configuration nodes. Let's explore pin control related properties to be used with client device nodes. For more information, you have to visit this section, pin control bindings.txt. But generally, we use these two properties, pin control -names and pin control -id. Let's first understand what is this and how to use this. This is nothing but the list of names. Basically, it's a string list property. List of names to assign states. This property is used to assign states, and the state name in this case is default. So the list of names to assign states, list entry 0 defines the name for integer state id 0. List entry 0 defines the name for integer state id 0. This is the integer state id 0. Basically, this defines the name of the state to be used with this pin configuration node. So if you're wondering what exactly is this default state and why it is required, remember that device may have different operational states. A device could be in normal state, it may be in default state, it may be in sleep state, it may be in suspended state, it could be in idle state. For your project, you can define different states. What these properties are saying is, if the device is operating in default state, then use this pin configuration values defined by this pin configuration node. If you want to put your device into sleep state, then you may use a different pin configuration node where the pin configuration values are written to support the sleep state. That means you can define different set of pin configuration values for different state of the device. Different set of pin configuration values. That means different pin configuration nodes to support different state of the device. A device state could be default, sleep, idle, active, etc. Different pin states help to achieve dynamic configurability of pins. For instance, in this example of WFROM, if the device state is default, then pins will be configured for I2C functionality. And if the device state should be changed to sleep, then the driver has to reconfigure the pins. That's what we call dynamic reconfigurability. The driver has to reconfigure the pins to support the sleep state. That's why pins will be configured as input to save power. So that means there will be two pin configuration nodes. One should be used with default state and one should be used when driver decides to put the device to sleep state. So take this example. Here, these are two pin configuration nodes. The first one configures the pins for I2C functionality and the second one configures the same pins for GPIO input functionality. You see here, so this node configures the pins for I2C functionality by changing the mode to 0. And this is another pin configuration node which configures the I2C pins to mode 7 and puts the pin to input mode to save power. So the client device will use the first one during normal operation, and when driver decides to put that device to sleep, it will use the second one to reconfigure the pins to stop leakage of current, thus achieving low power. That's why you see here the client device node will use the properties like this. Pin control names. There are two states, default and sleep. This is a list ID 0. This is a list ID 1. List ID 0 refers to the integer ID 0. This pin configuration node is related to this state, and this pin configuration node is related to this state, like that. When the driver decides to put that device into sleep, it picks this pin configuration node and it reconfigures the pins to support low power operation. It's like that. And this is how you claim the pin configuration node from your client device. Now in the next lecture, let's understand AM335X pad configuration macros. We have used some macros right here, so we'll explore that in the next lecture. Hey, welcome back to the lecture. So in the previous lecture, you explored the pin control subsystem of Linux, and we also explored some of the properties used to indicate the pin configuration in the device tree file. Let's understand how to write pin configuration nodes in the device tree and how to use the pin control related properties by doing an exercise. In this exercise, we are going to interface an 16x2 LCD to BeagleBone Black hardware, and we are going to test it by writing an LCD application. And that LCD application works on top of the GPIO sysfs driver what we implemented in the previous exercise. This is how our application works. We are going to use one LCD application in the user space, and this LCD application is going to deal with the sysfs GPIO attributes what we coded in our earlier exercise. The earlier exercise, you have created a device in a sysfs directory for each GPIO of the BeagleBone Black hardware, and you created two attributes for every GPIO device, that is direction and value. So this LCD application is going to act upon those attributes. It is going to use standard library system calls such as open, read, write to write new values into the attributes. And after that, whenever read or write is acted upon these attributes, you know that the corresponding store and show methods of your driver will get called. And those show and store methods of the driver will control the hardware GPIOs, isn't it? And thus we can control the LCD. For example, if the LCD application wants to send some data to the LCD, then it just writes that data to the value attribute. When something is written to the value attribute, the store method of the driver will get called, and the data then finally goes to the GPIO and it finally reaches the LCD. So before doing this exercise, let's understand how to connect the 16x2 character LCD to the BeagleBone Black hardware. You can make use of any of these available digital I/O pins. These are available digital I/O pins, and you can also take some GPIOs from this section, that is reconfigurable digital pins. But be careful when you are taking some pins from this reconfigurable digital section, because some pins are already used for some peripherals of the board. So we can safely use the pins which come under this section, LCD section. By default, these pins are actually used for LCD, but no LCD is mounted on our board. That's why we can make use of these pins as GPIOs. We can reconfigure them as GPIOs. So we'll see how to use these pins in subsequent lectures. First of all, let me tell you, these are the components you may require if you want to try it hands-on. If you don't have these components, then it's okay. You can just watch these videos. But if you really want to try it out at your desk, then you may have to procure these components. You just need 16x2 LCD. This is the same LCD what you use with your Arduino boards. very low cost component. And for the contrast setting of the LCD, you need one potentiometer, and for connecting wires you need one breadboard and some connecting wires, and of course you need a BeagleBone Black hardware. These are the pins we are going to consume on the BeagleBone Black hardware. So P839 to P845. These pins belong to the expansion header P8. This is the expansion header P8, and so we are going to consume these pins. I mean, you can use other pins of this section also. You can use these pins as well. You can use any of these LCD pins. Since the LCD is not mounted, you can use them. But for this exercise, I'm going to use these pins. This is how you should connect the pins of the BeagleBone Black hardware to the pins of the LCD. So this slide I have attached with this video. You can download and you can investigate. Basically, P845 is nothing but SOC's GPIO 2.6 pin. That is 6th pin of the GPIO controller 2. And P846 is GPIO 2.7. This information you can get from the reference manual. Just open the reference manual and open the section which is related to P8 expansion connector, and you will get these details. Now let's quickly see how to make the connection. So you need some jumper wires. You have to connect as shown in this picture. I have attached this picture with this video. Please download that. So all you need to do is, if you have an LCD, then take a jumper wire, connect a P8's 45th pin to the register select of LCD. So register select is pin number 4 of LCD, like that. And 46 to read write, 43 to enable pin. So we'll not be using data pin 0 to data pin 3. These 4 pins are not used because we'll be using LCD in 4-bit data mode. That's why digital pin 4 to digital pin 7 are used for parallel data transmission to the LCD from the BeagleBone Black hardware. And you have got 2 pins to control the backlight. Actually, we are not controlling the backlight. That's why just connect the pin number 15, that is backlight LED's positive terminal, so directly to the pin number 7 of the P9 connector, because P9 connector is ground. Oh, sorry. P9 connector 7th pin is actually, it gives 5-volt supply. That's why. So LED is positive, that is backlight LED is positive, you connect to the P9's 7th pin. So that gives you 5-volt supply. And same thing you have to connect as 5-volt supply to the LCD at pin number 2. So pin number 1 is LCD's ground. That's why that has to be connected to the BeagleBone's ground, which you can get at P9's first pin. That is ground. And LCD's negative should be connected to the ground pin of the BeagleBone Black hardware, that is P9 first pin. Actually, this is backlight LED's negative terminal. Very easy connection. You just have to make use of P8 and P9 headers of the BeagleBone Black hardware. So this is how you do the contrast setting for the LCD. Basically, you can use a potentiometer for the contrast setting, or any voltage divider circuitry using resistors. If you use a potentiometer, then this is how you should connect. The potentiometer actually has 3 terminals. Basically, these N terminals are used for connecting ground and power. They don't have any polarities, so you can interchange these terminals. You can either use this as ground or this as ground. It doesn't matter actually. Connect one end to the ground pin. So the ground pin you can derive from P9's first pin, that is ground. And this pin you can connect to the 5-volt supply that you can derive from the pin 7 of the P9 connector. And you can use this knob to change the resistance of this potentiometer. When you turn this knob, the voltage at this terminal changes. That's why that terminal has to be connected to the contrast pin of the LCD. That is pin number 3. If you have any multimeter, then you can just keep your multimeter between this pin and this ground. Then you see reading changes on the multimeter when you read the voltage when you change this knob. That's how you change the contrast of an LCD by changing the voltage at this terminal. So now let's understand the significance of LCD pins. We have got 16 pins on the LCD module. Now let's understand why these pins are used for. So we can understand this by going through the data sheet of the LCD controller. So the data sheet I have attached with this lecture. You can download it. So if you are using 16x2 or 20x2 or any other character LCD module, then your LCD module may consist of this Hitachi LCD controller or a similar one. The command set and the working principle is same actually. So you can refer to this data sheet without any problem. This LCD module doesn't communicate over any serial communication protocols such as I2C or SPI. Here we communicate through parallel data lines. If you browse through this document, you will see a section where the pin functions are explained. First, let's start with the VSS pin. This is the ground pin for the LCD module. So the ground pin of your board has to be connected to the ground pin of the LCD. And the next pin is VDD. So the VDD has to be in between, or VCC has to be in between a 2.7 volt to 5.5 volt. Basically, the BeagleBone board supplies around 4.5 volt to 5 volt, isn't it? That you can use as a power supply to the LCD controller. You can use a multimeter to check whether the voltage really falls under this value or not. That's a power supply to the LCD. After that, so this is a contrast pin. As I explained, here you should connect a potentiometer, okay, to control the voltage so that you can control the contrast of the LCD. And the fourth pin is the register select. Let's explore what exactly is register select, RS. So RS pin has to be controlled by the microcontroller unit or microprocessor unit. If this signal is 0, then LCD controller concludes that you are trying to send an instruction or a command to the LCD. That's the instruction register select pin. And if it is pulled to 1, then the LCD controller thinks that the user or the microcontroller is trying to send a data byte. That's why the RS line is used to differentiate between a command and a data. So that's why when you are sending any user data from your microcontroller to the LCD module, make sure that RS is pulled to 1 or high. For command, pull it to 0. And after that, next one is read and write. For this exercise, we'll not be using this pin actually. This will be always driven to 0. What's the significance of this pin? Read write bar. It should be pulled to 0, okay, if you want to write into LCD. And if you want to read from an LCD, then it should be pulled to high. The read write bar differentiates between write and read. So since in this exercise we will not be reading from the LCD, you can always keep this signal to ground. And after that, the next pin is enable. Enable, so it's a signal to the LCD in order to read the data which is there on the data lines. It kickstarts the data read write for the LCD controller. Basically, you have to do a high to low transition on this line. When that transition happens, the LCD latches or the LCD controller reads the data which is there on the data lines into its internal registers. Only when the transition is detected, the data will be latched inside the LCD controller registers. For that purpose, enable is used. So we'll see more details on that later. And after that, you have got 8 parallel data pins which carry data. This LCD can be used in either 4-bit data mode or 8-bit data mode. That means you can send 8 bits at a time to the LCD. In that case, you would need 8 pins connected between LCD and a microcontroller. This is used to write data into the LCD or to read data from the LCD. But for some applications, utilizing 8 pins of a microcontroller may not be practical. Most of the time, those many pins are not available on the microcontroller. At that time, you can use a 4-bit mode data transmission. In the 4-bit mode data transmission, you can only use 4 lines instead of 8 lines. That's why this LCD can be used in 4-bit data mode or 8-bit data mode. If you are using this LCD in 8-bit data mode, then all 8 data pins must be used. Otherwise, if you are using this LCD in 4-bit data mode, then you have to use only these 4 lines, that is DB4 to DB7. That means you have to split your 8-bit data transmission into 2. And after that, there are 2 other pins which are actually used to control the backlight of this LCD. Basically, this is a backlight LED's positive terminal and this is a negative terminal. So you can use it to turn on the backlight of the LCD. Now let's understand how to do this exercise. These are the steps you have to follow. First of all, connect the character LCD to the BeagleBone Black hardware as explained in the previous video. And after that, the second step is add required GPIO entries to the GPIO sysfs device tree node. So for the previous exercise, you actually created a device tree node to mention all the GPIOs which are going to be consumed by the GPIO sysfs driver. Now you have to edit that and add required GPIO entries. For this exercise, we are going to use these GPIOs of the hardware. After that, since you have edited the device tree file, you have to recompile the DTS file and make sure that the BBB boots with the modified device tree binary. And after that, load the GPIO sysfs driver. So for the driver, we are not going to do any modifications. Same driver as it is, we are going to use. Once you load the driver, so there will be a matching between device tree node and the driver, and the probe function executes, and in the probe function you actually create lots of devices under Bone GPIOs class. Make sure that all required GPIO devices are formed under this path. After that, I have attached the LCD application with this video. Download the LCD application files. There are 3 files: ledapp.c, led.c and gpio.c. I'll explain these applications later. Just download that, and you have to cross compile this LCD application and you have to transfer that to the board and you can test it on the hardware. In this lecture, let's understand this: adding required GPIO entries to the device tree node. Let's get back to the project. Now first let's edit the DTS file. Let's get into Arch ARM boot DTS. So let's open AM335X Bone Black LDD course.dtsi. Here we need to edit this. We have to create 1, 2, 3, 4, 5, 6, 7 GPIO entries. Let's do that. This is GPIO 1, 2, 3, 4, 5, 6. Sorry, these are for LEDs, so we have got 5. Let me create 2 more nodes. These are LED nodes. I would call them as just LEDs. LED 1 and this as LED 2. These 2 nodes we are not going to use. Those are for LEDs. Let's edit these child nodes. GPIO 1 label is GPIO 2.6. and after that this is 6. So that GPIO2 label is GPIO 2.7, like that you have to add. So I just completed here. You can see that this is GPIO 1, 2.6, 2.7, 2.8, 2.9, 2.10, 2.11 and 2.12. Totally there are 7 GPIO nodes and there are 2 LED nodes. So now we have to do one more important thing in this device tree node. In the previous lectures we explored about pin control subsystem, and we come to know that we use a generic pin controller driver of the Linux with our SoC to do the pin configuration, and that pin controller driver is based on device tree node. That means the pin configuration you have to supply through device tree node. That's why now we have to mention the pin configuration details for all these pins what we are going to consume, because these pins might have consumed by some other node and it could have configured it to some other functionality other than GPIOs. For our project, the pin has to be in GPIO mode. You have to ensure that. For that, you have to create a separate device tree node where you mention the required mode configuration for the pins what you are going to consume. So from this slide, we know that there are 3 types of nodes. First one is a pin controller node, which is given by the higher level DTSI file. And after that, this is pin configuration node. And after that, this is a pin configuration property, which is used to alter the mode of a pin. So now we have to create this node. After that, this is a client device node, which is going to consume the pin configuration node using these properties. We'll use this in our project now. Let's go back to the DTS file. This is a client device node. Let's first create the pin configuration node. For that, you have to add a child into the pin controller node. If you want to see the pin controller node, so just save and exit, just open AM33XX-L4 DTSI. Just search for AM33XX pinmux. Here it is. This is a pin controller node which will be handled by the pin control single driver, and it knows what is the starting address of the pad configuration registers in the SoC. You just have to supply an offset. We have to take a reference to this and we have to add a child node into this. Let's do that. Let's save and exit. Now let's get back to our DTSI file. So come out of this root node. This is a root node. This is this one. This is the end of Bone GPIO devs. Don't get confused. Bone GPIO devs. So this is actually the root node. End of root node. Here, take a reference to AM33XX pinmux, which is a pin controller node. Add a child node here. Here, let me give the name. Let's say Bone P8 GPIOs. Something like that. And after that, you have to create a property pin ctrl -single, pins is equal to angle brackets. And inside this, you have to mention 2 values. One is offset to the pins pad configuration register, and this is a value which is going to be stored in that pad configuration register. But instead of hard coding the offset of the pad configuration register and the values, so you have provided with some macros. Let's use them. Let's explore the macros. So the macro which you are going to use is this one, AM33XX padconf. This macro you can find in include DT bindings pin control omap.h. This is specific to the omap family of SoCs. All you need to do is you have to mention the pad configuration register offset here, and you can also mention the direction and pull up pull down control details here, because you see in our pad configuration register we have several fields, isn't it? If we go back to the pad configuration register, this was the pad configuration register fields of the SOC. First 3-bit fields you actually use to set the mode, and after that you also can do pull up, pull down resistor activation or deactivation. So the macros what you just saw also allow you to change these settings. And after that, in this last field you mention the mode. Valid values for the mode would be from 0 to 7. If you keep the mode as 7, then a pin is configured for GPIO functionality. And after that, this macro is implemented by this macro, where you can see that it finally turns out to be 2 values. This is the first value, this is the second value. That's what the pin controller property needs. It just needs 2 values. This macro converts the information what you supplied here into 2 values. Now the question is how to get these 2 values. I mean, we know that I can use 0 to 7 here, but how to get these values? For that also there are dedicated macros. You just have to use that. You need not to hard code any numbers here. First of all, how to get pad configuration register offset. For that, there is another header file called am33xx.h in include DT bindings pin control. And you see these are the offsets of pad configuration registers of various pins of the SOC. So you have to select the suitable macro from this list. So basically this macro turns that values what you supplied here into address of pad configuration register and the value. Now the question is, we know that what to supply here, that is from 0 to 7. How to supply values to these 2 arguments? Here you need not to hard code any numbers. You can again use the dedicated macros here. Now the first field, you know that this is a pad configuration register offset. Let's learn how to get this information. For this you have to think which pin of the SOC you are going to consume. How do you know which pin you are going to consume? Let's go back to the reference manual. For example, for this project, we are going to consume the 45th pin of the P8 expansion connector of the hardware. That is nothing but R1 pin of the SOC. This is pin of the SOC, remember that. The pin of the SOC which you are going to consume is R1. You have to check this R1 in the data sheet of the SOC to get its pin name. So let's go to the datasheet again. I have already shown this. Go to section 4 and go to the pin package ZCZ, so which is right here. So ZCZ package pins. Search for R1. R1, this pin, LCD data 0. Just click over that and it takes you to this table. R1 is a ball number and its name is LCD data 0 and its pin name is LCD data 0. Now what you have to do is you have to go to this header file am33xx.h and you have to use one among these macros. These macros are written with respect to the pin name what you just found in the data sheet, and these are register offset of their pad configuration register. Let's go to this header file. So let's save and exit. Just come to the Linux source tree, include DT bindings, pin control, am33xx.h. Here just search for LCD data 0. So that's why to configure this pin of the SOC, you have to use this macro, which points to the offset of the pad configuration register of this pin. I hope you understood how to find out which macros to used from this header file. Used from this header file. It all starts from identifying the SOC pin number and SOC pin name. Just come to this header file and search for the appropriate macro. Let me copy this and let me get back to the project. So I'll be using this macro now, em33xx padconf. em33xx padconf. After that, just paste that macro, em335x underscore pin underscore LCD data 0. And the second value you should mention here is direction. For that also you can use macros, which is there in the same header file, pin control em33xx.h. These are the macros you can use. If you want to set the direction to output, just use pin output. So if you want pin output with pull-up resistor activated, then just use pin underscore output underscore pull-up like that. For this exercise, I just want to configure the pins to output. That's why I would just use pin underscore output. Let's go back to the project, pin underscore output, and you can set the final value as 7, or you can also use a macro for this purpose. So here you can use mux underscore mode 7. So this macro you can find in omap.h, dt bindings pin control omap.h. Let's add the second entry. The next pin what we're going to use is GPIO 2.7, which is BeagleBones P8.46. P8's 46th pin is nothing but SOC's R2. R2 is LCD data 1. In the code you have to change this macro to LCD data 1 like that. Here what we can do now is let's add the second entry. You can add multiple entries between these angle brackets. That's why what you can do now is just hit enter here like this, and just hit enter over here like this. So in between these two angle brackets, add multiple entries. I'm just going to copy this and paste it 7 times. This is for LCD data 0, data 1, data 2, 3, 4, 5, and 6. So the last pin is GPIO 2.12. GPIO 2.12 is right here. Is right here, which is nothing but LCD data 6. That's why I have macros from LCD data 0 to LCD data 6. And after that, let's terminate this device node and also give one more semicolon here to terminate this pin controller node. Now for this node, let's give a label. I'll just call This device node, and also give one more semicolon here to terminate this pin controller node. Now for this node, let's give a label. I'll just call it as P8 GPIOS colon. And after that, in the client device, this is a client device, you have to make a reference to the pin configuration node. For that, we are going to use pin ctrl names is equal to default, and after that pin ctrl id 0 is equal to angle brackets, and you have to make a reference to this pin configuration node P8 GPIOS. Sorry, I did a mistake here. This is not pin control hyphen names. This is pin control single comma names. That's fine. Now let's understand how all these things work. First of all, when Linux boots on the machine, so first the pin controller driver will get executed, and the pin controller driver investigates all the child nodes of the pin controller node, and there is one child node inside the pin controller node. That's why the pin controller driver will assign all these pin sets to this device. It's like a grouping. It will assign all these pins to this group. Pin controller driver will not configure the pins to the value what you provided here. That will happen later. The pin controller driver assigns these pins to this group or to this device. The pin controller subsystem maintains all the pin details which are mentioned in the child nodes. And after that, when there is a match between a client device and a client driver, or a consumer device and a consumer driver, so prior to calling the pro function of this driver, the pin controller driver allows this device to claim this pin sets. Suppose if these pin sets are already claimed by some other device, then there will be a conflict. That's why there will be an error from the pin control subsystem, and hence the pro function of this driver will not get called. The pro fails actually. If no device is claiming the pin sets which are referenced by this configuration node, then the pin controller driver first configures the pins according to the pin configuration node. It just goes through these values and configures the pad configuration registers to the mode and these details what we have mentioned here. And after that, the pro function of this driver gets called. First pin configuration happens, then pro function of the driver will get called. That means once the control comes to the pro function, the pad configuration is already done. So the consumer driver can straight away, it can talk to the device without doing any further pad configuration, because it is already done by the pin controller driver. Please note that the pin configuration happens before calling the pro function of the consumer driver only if this property is set to default. If this property is set to some other values such as sleep or idle or something else, then the pin control subsystem of Linux won't trigger any pin configuration before calling pro function of the consumer driver. That happens only if this value is set to default. So the meaning of these two properties is this pin configuration node is used for default purpose, like that. So now we should note one more point here. These pins may be used by some other peripherals of the board. For example, this pin could be used by some other peripheral of the board like LCD or any other peripheral. In that case, there could be a conflict. between two devices. That's why you should never use a pin which is used by some other device tree node. In this device tree file, this pin is already used by the LCD. That you can see in a file boneblack-common.dtsi. If you check this, the boneblack-common.dtsi also adds lots of pin configuration nodes to the pin controller node. And here you can see that this NXP HDMI bone LT underscore pins, this node is already consuming these pins. It is actually configuring these pins for mode 0 functionality. That is the default functionality, that is LCD functionality. But on our board currently no NXP HDMI displays are mounted. We can disable this node. This you can use only when you have a HDMI display which is connected to the BeagleBone Black hardware. Let's see which client device uses this pin configuration node. Let's search that here. Just search for NXP underscore HDMI. Here it is. This client device is making a reference to this pin configuration node. That means the pins which are explained by this pin configuration node is claimed by this client device. What is this? Let's check this in the internet. What exactly is that? Basically, it's NXP's HDMI transmitter. The HDMI transmitter is using these pins. But since there is no HDMI displays are mounted on our BeagleBone Black hardware and we are not using that in our project, I can safely disable this device node. So if you are really using HDMI with your BeagleBone Black hardware and you are using this HDMI transmitter, then you may have to keep this device node active. In that case, you have to assign different pin sets to different device tree nodes. But for this project, I can safely disable this device tree node. That's why what I would do now is I just copy this label, just quit this and go back. And here, just paste that and make a reference to that and make status is equal to disabled. So you just disabled that client device node. Let's save and exit and let's compile this. The device tree file has been compiled. Now let's transfer this DTB to the board. I should execute SCP. And now we have to reboot the BeagleBone Black hardware. So because it has to boot with new device tree binary, isn't it? Now let's load the driver. Here it is. All these devices have been formed in the sysfs directory. Let's check sysfs class bone GPIOS. So now the LCD application is going to act upon the attributes what is there inside these devices, and that's how you are going to control the LCD. And just head over to sys kernel debug pin control and get inside this pinmux pin control single, and here just read this file. Just do cat pin groups, and here you can see that it shows grouping of pins. You can see that the pin number 40 to 46, that means SOC's pin number 40 to 46 have been claimed or used by this group. After that, just do ls here, and now let's read this file cat pins. Here you see values of various pad configuration registers of various pins of the SOC. So here these are pins of the SOCs. in which we actually consume from pin 40 to pin 46. These are the addresses of the pin configuration registers of these pins, and these are the values. And here you can see that the value is set to 2F. From that, we can notice one thing, that the last 3 bits are set to 111. That actually controls the mode. The mode is set to 7. That means the pin configuration value, what we mentioned in the pin configuration node, has affected corresponding pins pad configuration register. Let's go back to our steps. Now we have completed these steps, and now we have to do these 2 steps. Download the LCD application files attached with this video. In the next lecture, I will explain these applications. After that, we can cross-compile them and then we can test it on the target. I'll see you in the next lecture. Hey, welcome back to the lecture. In the previous lecture, you completed the device tree file modifications, and we tested those modifications with the driver, and we were successful in creating GPIO devices in the sysfs directory. And now we are going to test that using the LCD application. The LCD application consists of 3 files and its corresponding header files. So LCD app.c, lcd.c, and gpio.c. LCD app.c is a file where you write your LCD application logic. I mean the strings or message what you want to display. So we'll explore that in a moment, don't worry. And lcd.c is a file which gives all the LCD related configuration functions. For example, here the LCD application takes the help of LCD's function to configure the LCD, like that. After that, lcd.c takes the help of gpio.c to carry out the file handling of sysfs attributes. So we'll examine these files in this lecture. Let's go back to the project. The project is 007 GPIO sysfs. Just do ls here. You should keep gpio.c, gpio.h, lcd.c, lcd.h, and lcdapp.c in this directory. Alright, now let's explore these files, lcdapp.c, lcd.c, and gpio.c. So lcdapp.c is a LCD application where you can find the main function. What this application does is, it takes the user message and it prints it on the LCD. That's what this application does. So along with that, it also prints the IP address of the board, and it also prints the current date and time information. That's what this application does. And there is one more source file, lcd.c, which consists of all LCD handling functions like LCD initialization functions, LCD send command function, LCD send data function, etc. All LCD related functions are included in this file. So I will explain this file, don't worry. And after that, there is a gpio.c, which takes care of your sysfs GPIO attributes what you have created in the sysfs file system. Basically, it uses open, read, write system call to open, read, and write to the sysfs attributes what you have created. So first, the application starts with main, and here you see it first initializes all the GPIOs. So that's the first thing which is done by this application. These are the GPIOs we are going to use. Please note a small change here. Instead of P8.45, I have used P8.7 because I faced some issues with P8.45. That's why I thought you may also face the same issue. If you face any issues on P8.45, then change it to P8.7. That is actually GPIO 2.2. So that is used to control the RS pin of the LCD. What we do inside the init GPIOs is very simple. We first configure the direction of the GPIOs. GPIO configure direction. So this function is implemented in GPIO.c. Let's go to the GPIO.c. Here it is, GPIO configure direction. It just takes the GPIO label. GPIO's label are, open the GPIO's label. So it is there in GPIO.h. Oh, sorry, not in GPIO.h, that is in LCD.h. These are the labels. It takes that label here and the direction value. The direction value could be 0 or 1. What this function first does is, you see, it opens this attribute, the direction attribute what we have created. So the sysGPIO path you can find in GPIO.h, which is a macro which is set to sysclass Bourne GPIOs. Basically, we open this file, the direction attribute, by using open system call in a write only mode. And after that, we write either out or in, depending upon the value of this direction value. That's how you change the direction of the GPIO. So when this is done, you know what happens. Your store method of the driver will get executed and the GPIO's direction will be made as out. So that's what happens from this LCD app.c. The direction of all the GPIOs are set to output. And after that, GPIO's output value is made as low. That's what init GPIO does. Let's go back to the main function. After that, there is a small delay. That's it. And after that, you take the message from the user and store it in message buffer. That's a character array. And after that, here we start the LCD init. This LCD init is implemented in lcd.c. So here it is, LCD init. If you want to understand how exactly this LCD init is coded, you have to refer to the datasheet. This is coded exactly as per the datasheet. So the initialization sequence of the LCD is already explained in the datasheet. You have to refer to the page number 46, figure 24 in the datasheet. Let's see. Just go to this section, initializing by instruction. Right, so there is a flow chart actually. This is the flow you have to follow if you want to initialize an LCD in 8-bit interface. But we are not using 8-bit interface for this exercise. We'll be using 4-bit interface. That's why you have to refer to this figure 24. So this is power on of the LCD. After you power on the LCD, you have to wait either 50 milliseconds or 40 milliseconds. Let's take the bigger number, so wait for 40 milliseconds. Once the VCC of the LCD controller rises to 2.7 volt or 4.5 volt, the LCD will start doing its internal operation. That's why the user should wait, or the microcontroller should wait for at least 40 milliseconds before sending any command or any data to the LCD. And after that, you have to send this code 0011 on the data lines DB4 to DB7. Please note that for this exercise, we will not be using DB0 to DB3. Why? Because we will be using the LCD in 4-bit interface. When it is used in 4-bit interface, DB0 to DB3 lines are not used. Only DB4 to DB7 lines are used. Next step, what you have to do is you have to send this data onto these lines. So that's what done here. First, the LCD init function waits for 40 milliseconds. In Linux application programming, you can use this function, usleep, sleep for microseconds. And after that, send this data 0011, that is 3. So you see here, a data byte 3 is sent. But before that, since you are sending an initialization command, isn't it, to the LCD, the RS line must be pulled to low. And after that, read write has to be put to low. Why? Because you are writing into the LCD. You are writing an initialization command. That's why RS must be 0 and the RW bar should be 0. That we do by using GPIO write value. GPIO write value is again implemented in GPIO.c, and you see here we now open the value attribute by using the open system call, and we write either 1 or 0 to this attribute value, which is there inside this sysfs path. So write 4 bits. The data byte is 0 cross 3, and where this is implemented. So this write 4 bits is implemented right here. Here it is, write 4 bits data. I just use GPIO write value again to write into these GPIOs. So this is basically a parallel data transmission where you are writing 4 bits of information to 4 different lines at a time. After that, you have to do LCD enable. So I'll come to this later. So we'll understand what is its significance little later. All this function does is it just writes 4 bits to 4 different GPIOs, which are used to connect LCD's DB4 pin, DB5 pin, DB6 and DB7. And after that, you have to wait for more than 4.1 milliseconds. That's why I am waiting here for 5 milliseconds. And after that, you have to again send the same code 03. So that's why I'm again sending that code here. And after that, you have to wait for more than 100 microseconds. That's why we are waiting for 100 microseconds. So basically they say wait for more than 100 microseconds. You can make it as 150 here. After that, you have to send again that code, the same code 03. That's why again I'm sending here. And after that, you have to send the code 02. That's why I'm sending the command 02 here. After that, you can send the command. These are the commands. So we'll understand what are these commands. These are configuration commands of the LCD. But up to here, you have to do as per this flowchart. These are the custom commands. So I will cover that later, how to create a custom command. But up to here, you should follow this flowchart. Very important. So if you don't follow this, then your LCD may not work properly. So that's about LCD initialization. In the next lecture, let's understand how to create a command code and send it to the LCD. I'll see you in the next lecture. Hey, welcome back to the lecture. In this lecture, let's understand LCD commands. So how to create an LCD command and how to send a command or a data byte to the LCD. We should create LCD commands which we can use to initialize and control the operations of the LCD. Remember that a command is of 8 bits long. There are various LCD commands you can create. LCD commands you can create to function set. You can control the display. You can control the cursor on off, the blink control of the cursor. You can decide the entry mode. You can clear the display of the LCD. You can set coordinates, activate or deactivate display shifting. So various things you can do by sending commands to the LCD. Let's understand how to send a command or a data to the LCD. So a command or a data byte is of 8 bits, that is 1 byte long. You can send all 8 bits in one go over 8 data lines, or you can split into 2 data transmissions of 4 bits each. Basically, we are going to use this method in this exercise. So we are going to split a byte into 2 data transmissions of 4 bits each. For 4-bit data transmission, you only need 4 data lines connected between LCD and the microcontroller unit. That means for 4-bit data transmission, you must use the data lines D4 to D7. Please note that. So that means DB0 to DB3 is not at all used. when you use the LCD in 4-bit data transmission mode. This picture I have taken from the datasheet. You can learn more about these data pins in the datasheet. How to send a command? First, you should create a command code. I'll teach you later how to create a command code. And after that, make the RS pin low. Why? Because you are sending a command. Read write pin should be low because you are writing into the LCD. After that, first send the higher nibble, the higher 4 bits of the command code to data lines. After that, make the LCD enable pin high to low. This is very important. So you send the 4 bits here, and after that you have to make LCD enable pin high to low. When LCD detects high to low transition on the enable pin, it reads the data from the data lines. This 5th step is very important. After that, send the lower nibble of the command code to the data lines. And again, you have to make LCD enable pin high to low. And after that, this is again very important. You have to wait for the instruction execution time. Once you send the command, LCD will be involved in executing that instruction. That's why you have to wait until the instruction execution time is elapsed. That instruction execution time is mentioned in the LCD datasheet. Otherwise, there is one more method. That is, you have to read the busy status of the LCD. Busy status of the LCD can be read on the D7 pin. If that pin's status is high, that means the LCD is busy in doing its internal operation. That's why either you can check the busy flag or you wait by giving some delay until the instruction execution time has been elapsed. So let's say your command code is 0x28. This is a binary format of that. And this is a connection between MCU and the LCD. So 4 lines are used, D4 to D7. First, you have to send the higher nibble. This is the data of the higher nibble. So the 4th bit you have to send over D4 line, 5th bit on D5 line, 6th bit on D6 line, and 7th bit on D7 line. So after that, you have to send the lower nibble. So the 0th bit has to be sent over D4 line, the 1st bit has to be on D5 line, D6 line, and D7 line. So that's how you should send. That's what done in the program. I will show you that. Let's go back to the lcd.c and you see a function lcd send command. First, rs is made as 0, rw bar is made as 0, and write 4 bits. The higher nibble is extracted by shifting the command code to right side. Let's go to the write 4 bits again. So write 4 bits. You see here. So the least significant bit of this data is sent over D4. If you consider this higher nibble, then this is the least significant bit, isn't it? That is sent over D4 like that. So D5, D6, D7. Once you send a nibble to the LCD, you have to make LCD enable. That means you have to make a high to low transition on the enable pin. This is actually explained in the timing diagram of the LCD data transfer. If you go to the LCD data sheet, if you go to the page number 22, so here you see it shows how the data transmission should be done. Let's understand how to send an instruction or a command. Here IR means instruction. First you send the higher nibble 4, 5, 6, 7. Once you send that, see this enable pin. You should make high to low transition. And after that, you send the lower nibble IR0, IR1, 2, 3 and make a transition high to low. Once you send the instruction, a complete instruction of 8 bits, then you have to wait. Wait for the busy flag to reset. Or if you don't want to check the busy flag, then you can wait for some time as suggested by the datasheet. And after that, you can send any data or another command. If you want to understand instruction execution time, then you can go to the datasheet page number 25. Here they have explained the instructions. There are various instructions like clear display, return home, entry mode set, display on off control, and at the right hand side you can see the execution time. So if you don't want to check the busy flag, then it's fine. At least you have to wait for these many microseconds. I hope you get some idea about sending a command. So that's what done in the code, okay? When you send 4 bits onto the data lines, we call LCD enable. What this LCD enable does is, it is implemented right here, LCD enable. It makes high to low transition. Here it is. It makes a high to low transition, and after that, wait. I just wait for around 100 microseconds. Basically, any value which is greater than 37 microseconds would be fine, because it says the instruction execution time is 37 microseconds for some instructions. For these instructions, the instruction execution time is little high. You can see that it is in terms of milliseconds. I hope you get the idea of sending command to the LCD. You just have to keep in mind this timing diagram. There is one more timing diagram. Let me show you that. So here there is one more timing diagram which shows how you should do busy flag check if you wish to do busy flag check. You see here, you send the data here. So once you send the data, you should make enable pin low to high transition. Once you do the low to high transition, the internal operation kicks in. That's why LCD will be in busy state. It will be doing its internal operation, functioning. That's what it says. You should confirm the busy flag that the busy flag is not set. After that only you can send next instruction. So if you don't want to check the busy flag, as I said, wait for some time. So just give a wait, blocking, wait, and you can send the next instruction. In this application, the busy flag is not checked. Instead, we wait by using the useLeave function. Now let's understand how to send a data byte to the LCD. It is very similar to the command code. First, you have to make RS line high because you are sending a user data now, and make RW bar low. First, send the higher nibble of the data to the data lines. Make LCD enable pin high to low. Send the lower nibble and make LCD enable pin high to low. Here there is no wait actually. Why? Because it is not an instruction. That's the user data. Let's see how it is implemented. In the lcd.c, you see a function LCD send data, or the function name is LCD print char. So it receives 8-bit data here, and that 8-bit data is broken into 2 data transmissions of 4-bit each here, and you first make RS is equal to 1, RW bar 0. First you write the higher nibble, and after that the lower nibble. Just go through these codes, so if you want more information. And in the next lecture, let's understand how to create a command code. I'll see you in the next lecture. Hey, welcome back to the lecture. In this lecture, let's learn how to create an LCD command code. For that, you have to visit the page number 24, okay, where they have explained the instructions. Let's say you want to send a command to clear the LCD. Then you have to send this command. This is a command of 8 bits. Command code will be 01, isn't it? So if you see this command, if you just split this command This is 0, this is 1. So the command code will be 0, 1. How you will be sending this command to the LCD? You first send 0. So first send 0, and after that high to low transition on the enable line, and after that send 1, high to low transition on the enable line. So once you send the command, then wait for the instruction execution time. The instruction execution time for these two commands, for clear display and return home, is 1.5 milliseconds approximately, and then you can send the next command. After that, return home. So what this command does is it sets the DDRAM address to 0 in address counter, also returns display from being shifted to original position. Basically, it brings back the shifted display to the original position. That's why it is called as return home. So if you want to understand any instruction or any command, just go to the datasheet and just search for that command. Let's say return home. The datasheet explains that command. How do you create the command code for this? Again, so let's divide this into nibbles. This is 0 and this is 2. This is don't care here. So after that, let's understand entry mode set. This entry mode set command decides cursor's move direction as and when you write the data. And it also controls shifting of display. These two fields are configurable. You can configure according to the information given here. ID is equal to 1 means increment, 0 means decrement. So that means when you start writing data into the LCD, the cursor automatically increments to the next position or decrements to the next position. So let's say I want to increment the cursor as and when I write the data to the LCD, then I would use ID is equal to 1.